The other thing that you can be aware of is your depth of cut. So fairly straightforward with side turning. Really, you want to avoid going over about 3 millimeter or 118 thousandths on side turning. Side turning is a function of grooving inserts, but grooving inserts are they're not a replacement for some other iso turning type operations. They can be if you have a very shallow material to remove, but just keep in mind that you want to keep it under 118 thousandths or about 70% of the insert width. So as the insert size gets smaller, you want to watch out for that. We recommend really with side turning, you want to look at an insert width of 4 millimeter or greater. So for 157 thousandths or greater, then look at side turning. Doesn't mean you can't do it with a smaller insert, but 4 millimeter and up, you're going to have a rigid, strong pocket that won't move around when you're side turning. The other thing is pay attention to your minimum width. So minimum width is important, or minimum depth. So your AP min, because you want to be more than the radius whenever possible. Because if you're just turning and you're turning on the radius, below the radius line here, then you're doing a lot of pushing. So the force directions are different, and you're not really keeping the insert down on the material. So it's trying to push it away. So always cut above the radius when possible. You always want to make sure to kind of have an eyeball on whether or not your insert is 90 degrees to your cutting plane or your axis of rotation. One way to see, a quick way to see if your tool is aligned correctly is if you have vibration in one direction and not the other. So for instance, if you're doing a plunge and turn and you have chatter or vibration in one way and not the other, chances are your insert is heeled out as shown here. So you always want the heel up. Think of it, like a foot here. You want the trailing edge of the insert opposite the feed. You want that to be heel up and not heel down, as you see here. It's always better to be heel up in the case of side turning. Pay attention to your overlaps too when you do a plunge. So not turning overlap, but when you're doing a plunge, best case scenario is 2 times the radius for your overlap. That's a good rule of thumb that will help you eliminate leaving little upstands of material or any problems. High pressure coolant. So high pressure coolant is a very effective way to improve tool life. So I've seen a test where you can improve tool life by 6 times by implementing a through coolant insert with high pressure. Mainly you have high heat cycling. So when you have cooling getting right under and into the cut zone, you're really heating the chip and cooling the chip very quickly. So that helps with chip breaking. Variable pressure and volume is a plus. So if you have one of the more sophisticated cooling systems, you can play with the pressure and the volume of the output so that you don't just have vapor coming out of the coolant hole. You have actually a laminar flow of coolant, and that's going to give you the best cooling and the best chip breaking. The other point to that is in grooving especially, really the part limits access of the coolant to the cutting zone, even more so than a turning operation. So just think of it in those terms, having through coolant inserts, why that is so beneficial, because when you're in a deep groove, coolant is being blocked, partially by the part itself. So always be aware of that. Stability. So stability with tools is important. you'll find some of our tooling systems, depending on the insert size, has a pin to help stabilize this clamping so that you're not rolling the insert. And also keep in mind that every millimeter counts. So having a tool that holds the same insert and you have a shorter and a longer version of that, so that if you're doing a shallow groove, you can use the shorter version and you have the longer version for a deeper groove, is beneficial because you're conserving that distance from the fixing and getting the best stability. So don't try to have a tool that's really long so that you can do all the different grooves that you have in your product mix, but just choose several different ones so that you have the right stick out, and every millimeter counts. Cutting speed. Cutting speed is important to focus on. So if you look at your flank wear and your cutting speed, so VB is your flank wear, VC is your cutting speed. Cutting speed has a lesser effect on the chip behavior than feed, but the proper amount of heat can cause the chip to self-break. So it does have an effect. If you have good coolant going to your material and to your cutting edge, and then you have a little bit higher cutting speed, sometimes you can cause the material to break a little easier. So as mentioned before, don't use a cutting speed parameter that's too low, because you're diminishing your return there. You're not getting good productivity, and you may have built up edge, which is breaking down your cutting edge even faster. So your edge economy is much less. Using a cutting speed on the other side that's way too high can cause thermal deformation of the carbide. So if you get this carbide hot enough for long enough, it will most definitely deform. And once that deforms, it cuts in a very negative way, and you can break your cutting edge. A lot of times I've seen people misdiagnose chipping issue as a feed issue when they were actually just using too high of a speed. The edge was deforming, and then they were saying, "Oh, my feed must be too high because I'm chipping," but the chipping was actually caused by the deformation of the edge and then the immediate breakage of the edge. So always keep your speed parameters within reason. And the VC, as that's increased, just know it's physics. It cannot be changed. That as you increase the speed, the tool life decreases. So just keep that in frame. If you do have a situation where you have a chip control issue and you've applied one of our chip geometries and you're still not getting good chip control, you can implement a process called speed Peck. So speed Peck is a way to sort of cheat the system, where you can use any applicable cutting edge, and you just use your program and process to break the chip or make it smaller and more manageable. So the first thing is you would look at your groove and divide that into 15 thousandths depths per plunge, for instance. And then after each plunge, you just retract half the feed rate. And that's really, some people use the full feed rate. It's a matter of preference. But if your machine is accurate enough, then use the full. If it's not, if there's some slop, and you may roll a chip back under the cutting edge, or have a problem with chip recutting, then use half of the feed rate. And then you just repeat that process using a macro or a can cycle until the depth is achieved. So it's just like Peck drilling. If you're using an old school like jobber drill, You're just pecking out the material. You can use dwell, but just know dwelling actually, you're applying more heat than is necessary and can wear your insert out faster. So pecking is better than dwelling, but dwelling is also possible. All right, last slide here, and this is just a quick troubleshooting guide. So symptom, not on center. Within the GPS system, you can install a new top clamp and check the machine alignment. Check the holder clamping, check the holder for any kind of damage. Breakage, check the center height, check for clearance issues, check decrease the cutting parameters, and check for chip recutting or jamming. Cutting speed is not usually it's not usually going to cause a breakage. You really have to have an excessively high speed to cause a breakage of your insert or tool. It's usually related to a clearance issue. So whenever you have a breakage on an insert, look for clearance issues as a primary cause of failure. Excessive wear, reduce your speed, check the center height. Chipping, generally check for chip recutting, reduce your feed, increase your coolant pressure. Poor surface finish, use a shorter length, increase speed, increase the tool radius, because we know the tool radius and the feed are the two primary factors involved in surface finish. And then reduce your feed, use ground profile, or check or check tool alignment. Poor chip control, use a chip breaker. We have, I think, over 26 different geometries available in the Horn 224 and the 229 system. So make use of those. Use speed peck. Take multiple multiple plunges. So use a smaller insert and take multiple plunges. Increase your feed. Built up edge, increase the speed, check coating compatibility with the workpiece. Kind of, pull a loop out, look at your cutting edge. If you're, running an aluminum material or brass or something sticky, look at your cutting edge. Is it sharp enough? Is it designed sharp enough? So a lot of horn tools are designed to be very, very sharp because we don't have to take huge interrupted cuts as a general rule. So not usually an issue, but you can check that and make sure that the edge is sharp enough. Edge deformation, the remedy there is decrease speed. So decreasing your speed is usually going to fix any kind of edge deformation. All right. And the last is, don't forget, you have a great tech support team within Horn that's available to you. So don't forget to contact them if you have an issue. More than happy to help. And then also don't forget the application and sales engineers out there in your areas. They also will be happy to help you if you're having an issue with Horn tools.